Great. Hi, everyone. I'm David Rogers from ORNL's National Center for Computational Sciences. This part of the BSSW tutorial addresses software testing and its relationship to the development process. See if I can switch slides here. As you can see from our tutorial schedule, software testing is divided up into two smaller talks. Part one covers the context for creating a testing strategy, and part two will provide guidelines and experiences from our teams. Ideally, testing is one facet of the software design process. So after we get our feet wet in this talk with simple testing ideas, the next talk, very next talk will cover software design, and we'll come back to testing again with more in-depth discussion. Software development for science is a complex business involving expertise in many different subject areas. Rather than go through all the parts of this slide, suffice to say that if you have a large code with many moving pieces, then testing should be an integral part of moving your software project forward. For the project team to work together effectively, you need to iterate on features that move towards the science objectives. And I would argue that testing happens automatically and naturally. However, it's not always recognized and archived in a way that lets it be reproduced later. This last thing, the recognizing your test as a test and turning it into something formal is critical, since otherwise the tests can be lost. During initial development, functionality is tested as it's added. These activities should be recognized as tests and stored for future use. Especially important are synthetic use cases that check the accuracy and stability, as well as the models themselves. It may take some extra work, but it's very worthwhile to design data structures that allow your algorithms to interoperate with each other, and also to save that information in the form of tests. After development, those tests become even more important. They help to check whether the behavior of your existing codes is still functioning when adding new capabilities. They also serve as baselines and checks when you're upgrading your existing algorithms. For example, hardware vendors are usually willing to help accelerate your algorithms as long as they have a good test suite to check their optimization work. It's very hard to work on someone else's code and add something that makes it faster without also having a test that lets you know how fast the thing is going, and if you have inadvertently introduced bugs. Tests also show your project status, and they can help direct your code maintenance activities. And they're also critical when preparing a production release of your code to the community. So no matter which Git workflow you choose, eventually you should be taking all of these things that you've added into your code and push them to a final published release of your code. And when you do that step, you want to be able to say that there's some level of testing on each one of the pieces of your code. So testing plays an integral role in the software development process. Here's a summary of practices detected by some GitHub repository scanning associated with groups developing scientific software. About half, so these bars are showing you, 0% of the repositories have this thing on the left, 100% have them on the right. About half the project have README files. And I didn't go into depth on how I detected tests, but I looked for a file named test. And if you look for any files in a directory or a file name with test in it, you see that about half the repositories have something called test. It's a little bit smaller than the number of repositories that have some sort of build process that's identifiable, like a CMake list or a makefile. So the scientific community recognizes that putting something that will test your code is important. Unfortunately, I don't have the ability to drill down and find out exactly all of the different types of tests people are using. But it's definitely something that the community recognizes as important. This presentation will hopefully have some useful advice for each of the following groups. Those new to software testing can find advice for getting started. Those working with legacy projects that need a testing system, as well as practitioners who are looking to improve their testing strategy, should also benefit from the explanations below, plus the examples that I'll present in the second half. So let's get into definitions. There are many kinds of tests, and entire volumes have been written on the subject of testing your code. Here, I'll point out that the purpose of tests are to build confidence that your software is doing what it's supposed to do. There's a theorem called the Curry-Howard isomorphism that states that programs are proofs, and proofs are programs. So every step in your program is building something up. Tests are a part of a verification process that check that each module of your code is building the mathematical object that it's supposed to. The verification process needs to look at all those little steps and show that the steps work as expected. Tests are the implementation part of that process, where verification can check steps in the proof process. So verification can check the steps in the proof process, but validation is a little bit harder. Validation is, I tend to think of it as more of an outward-looking process that asks whether your science domain is covered by the models and algorithms that you've implemented. That actually goes a little bit beyond testing, but it's good to keep in mind that tests are part of a validation process that stretches from checking and verifying your implementation all the way through making useful conclusions about your problem. A correctly implemented code can actually prove or disprove a scientific model. So it's important to have all of those tests and concepts in mind that you're going from a code all the way up to a model, and you want to be able to verify every step. Following this Curry-Howard isomorphism, you might ask, what does a program prove? A program actually proves something like, for all A following assumptions X, there's a B such that Y. Or in other words, A and B are the program's inputs and outputs. They come with lots of conditions attached to them. An input-output statement like that, your program starts with an input and creates an output, should hold for individual units of the program, as well as for combinations of those units. So the schematic on the right is showing kind of like the top level view of everything in your code. And at the bottom level, you've got smaller units of code which have simple inputs and simple outputs. Most conditions on the inputs, which I called X earlier, are easy to list, but sometimes additional ones show up midstream or in the middle of your program that you should also keep track of. So you may have a module which requires some very specific conditions hold on your inputs. It's good to keep track of what those requirements are, and if possible, kind of make them a globally recognized piece of validation for inputs. Similarly, there are important conditions on the outputs that you want to check. They include the easy things like, am I building the object and does it have the invariance that it's supposed to have? But then there's also higher level things about what your code should be doing, like, is it convergent to the right answer? Is the stability and accuracy of my code what I think it should be from the mathematical model? Tests at both the component level and the systems level are needed. There's not a strict divide between those levels, but they're often termed unit and integration. So I put kind of unit at the bottom as a simple thing that you can test, and an integration test at the top as a kind of a high level thing that tests multiple modules working together. See if I can check my time. I'm good on time. Okay, so research, now that we've covered kind of the definition of tests, let's talk about the challenges with research software. Research software has unique challenges as compared to industrial software. In fact, even in big tech industries, if you ask the research division, what are your requirements for testing research software, they won't be able to give you a concrete answer. That's because research software explores areas where we don't yet know the expected outcome. After all of the expected behavior has been checked, we have to rely on domain experts to help validate the model and iterate on design. So those are kind of the challenges with exploratory software. Legacy codes have more definite expected behaviors, but if the tests have been lost in the midst of time, then adding new tests is a difficult problem. It's necessary to re-examine the original assumptions about the inputs and ask about their effects on which parts of the code are being exercised. Often it can be difficult to tell how parts of the code interact and what everything is actually supposed to be doing, which I'm exemplifying here as the question of looking at a piece of an old code and asking, is this bad code and poorly written? Or is it something that fixes, it's a necessary evil that we had to put in to fix an interaction or combination problem? And there are different challenges still when you're looking at releasing a piece of software. Usually what is wanted is a thorough code review to verify that each part of the code addresses the intended use case. Verification is a very cost-effective way to ensure that the code defects don't get through all the way to your customer. So I'm going to end this section with some quick, hopefully inspirational examples of how to get tests into your daily workflow. It's not really as hard as it seems. If you've written a function before that checks for errors, you can actually turn it into a test without too much effort. Here's a scaffold framework, specifically for Python projects. What it does is it generates a setup.py and other files associated with Python's build and test process. So what I'm showing here is just the two commands that you would need to grab PyScaffold and another helper program called tox from the Python repository. PyScaffold gives you a new program called PutUp, which lets you create a new project of your own name. So here I'm showing the creation of example projects called AutoQCT. If you now change directory into this AutoQCT, you'll notice that it's just a scaffolding. It's a bunch of setup. It's a setup.py file plus a bunch of metadata about how to build and test that AutoQCT project that I've just created. And here, out of the box, is the example of running the tox command. When you run the tox command, it will do some checks and print out the versions of the Python modules that it's using. And after that, it will show that it's actually exercising some test skeleton py files that it's created here with the famous Fibonacci function that computer scientists love to test things on. What this thing is doing is, if you go and look at the test skeleton.py, or you follow these examples here, you can look at the test skeleton.py file. And inside there's a simple function which has an assertion, and it asserts that the Fibonacci function is giving you the answer that it's supposed to. So using this scaffold, you can use it to put the structure of your tests into some definite order and reproducibly run it with some very simple top-level commands. There's one of the best things about the PyScaffold project is that it has a lot of documentation on how to use it to insert into your own code and ways that you can go about adding and testing. It also includes helpful hints for building your code with the Python build system and sending it out over to the PyPy repository. And it also includes documentation, which I'm not covering here, but it's useful to have a scaffold to put documentation into your project. You may be asking, what if I don't have a Python project? What if I have a real C++ or compiled code? And now I want to point out that there's something similar called the BLT, or the build link test environment. What this is doing is it's providing you a set of CMake files. CMake is, in a lot of ways, like a successor to the auto tools, or kind of a competing product to GNU auto tools. And if you want to go past make files and start to generate your make files and build by inspecting some of the configuration on the system, you'd be looking at building CMake code. This CMake scaffolding in particular can be added into your code fairly easily because it's meant to be added as a subdirectory. So here in the top left, I'm showing the CMake file for my top level program. I created an empty directory and just typed these 5 lines into the CMake list file. And the include BLT setup blt.cmake is where the BLT framework is included. Once I've created this, I can make a build directory and build it. This is the standard process for building something with a CMake file. And oh, looks like I forgot to run the CMake command. But in any case, put a CMake ... here. I'm out of time. Anyway, put a CMake ... here. And once you've run your CMake, then you'll actually see that BLT includes some default tests as well. Both of these projects don't give you tests for your own project, but what they do is they give you a framework to put your tests into. BLT has really useful documentation as well if you want to use the Google testing framework or something else called, I think it's Fruit for testing Fortran codes. So that's C++, C, and Fortran can all be handled with BLT. Going farther, there's a lot of extra pieces that you can do, and I don't want to go too much over time here. So I'll also point out that there's a copy of these presentation slides on Figshare that was shared earlier. And I think there's a link inside of the questions. There are ways to go farther, and you can do things like static code coverage and analysis. You can get graphical code coverage results. And that's a way to help you look at your project from the test's point of view and see which parts of the code are my test exercising. And they can give you really useful things like line-by-line details. To give a quick summary, productive software teams should always be checking their work. The time taken to save those tests is well worthwhile. There are different challenges associated with testing different kinds of codes, and you always want to be making a testing strategy that makes the most sense and provides value for your team. Don't get distracted by having too many technologies out there. Find something that works and exercise your code with it. With that, I think I will conclude the testing section and